Hey, how are you all? Welcome to this one of the last days of this Global Hack Week. It's quite a journey, to be honest. I think this is one of the most exciting ones I've been part of. I really like the streams I gave this Global Hack Week, and also I really have enjoyed a lot spending time with you all. As my favorite part of this stream, let's start reading some comments. Mohit Jepping says, "Hi Alberto, hi Rainson. It's 12 a.m. stream. Let's go." I don't know for you, but I really like Sparky Certain Student here. It is 10 p.m. for me, so I'm tired too. I know that feeling, bro. But also, hello everyone. Before everything, um, another um, happy hand, let's say, for Mohit Chopping. It's my first time to explore AI machine learning. This is amazing. So I will do a little recap for you because this is not that simple topic. So What I recommend you is to watch my stream from past Friday, in which we explore a little bit more of the theoretical um, idea of what artificial intelligence, machine learning is, the difference between these two, because they are not the same, deep learning, for example, etc. I teach AI safety. Reinforced learning, it's something we talk about a lot, but I thought it will be great to hear some refreshers on it. Oh, that's amazing. Thanks for being here, trying to learn. I hope to give a great insight here about this topic. Well, returning to the suggestion for mojito chopping, the that the stream it's on the recordings, so you can watch it on the YouTube channel from the Merely Hacking. Um, what else? Well, why not? Let me say that if you missed some other of my streams, you can watch it. You can watch it there. Um, we also give. Sorry, I say we because you are part of this too. But I give a session on how to use MATLAB neural network designer. It was a two video series. Then yesterday we closed the day with a stream on how to implement quickly TensorFlow just in an app to make a text analysis and answer some questions based on that context. So those are some of the topics we cover already. And right now we're going to talk about reinforcement learning, right? So I see here for Rainzone that he teaches or she teaches um, AI safety. So that's really cool. Like, do you teach like safety in technical way or also in like ethical things? That will be another very interesting thing. Let me know. Well, uh, what is reinforcement learning? There are two approaches we can say. Um, the first one is trying to explain what is reinforcement learning under the context of AI. Remember, artificial intelligence, it's all that tries to emulate intelligence at all. There are many ways of intelligence. These algorithms can replicate how we think, but the specific part of this um, being that wants the machine to learn, it's called machine learning. Very intuitive, right? Well, reinforcement learning it's also very intuitive because it's a type of machine learning that, as the name says, it's based on the mere idea of learning under reinforcement scenarios, like trying to maximize the how to say the reward of an action, um, and this is like the very first way we think um, the computer should learn, because we start doing this before for computers for animals. I mean, again, I don't want to promote um, like animal suffering or these things, and I don't agree with animal testing, but essentially we do this, like for example with rats, giving them pieces of cheese if they complete a maze, or with horses when they gave a good run, etc. We gave them apples. So um, this experiment where they have a monkey, and if they press the correct button, they will receive a banana, and etc. 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 Well, this way of thinking, the learning, it's it was like one of the first preconceptions we have about this machine learning. But it was not until recent days, thanks to the advances in computing, that we can make this possible. Because remember, we as humans also learn this way. Like if you do something wrong, you will be punished, and if you do something right, you will be rewarded, right? In this same sense, the machine does the same, but in this case, it is not the parents of the algorithm or the system, the artificial intelligence, the ones that, how to say that, decrease the punish or the reward. It is us, the programmers. So let me see. I see a comment here. So essentially, the part I tackle it's technical. We read some approach papers from, no, some research papers from OpenAI and Anthropic. Different researchers talk about risk, look at failure models, and possible solutions. This is really cool. Where do you work? That will be very, very interesting to know. Um, I don't know. I'm wondering your company does like consulting, or it's like they on your work you have like a dedicated department for the things they do on the company. I'm guessing this is like consulting because it's so specialized knowledge here, which is great. Again, nice work. Okay, returning to the reinforcement learning. So, for those who are their first time exploring these artificial intelligence machine learning, I hope you now are more like you now know where we are step on, right? So again, artificial intelligence, machine learning, reinforcement learning, and reinforcement learning. Again, the idea of that we learn by interacting with the environment, and these give us like the natural way of learning. It's way too old, and this reinforcement learning, what we want to do, it's to maximize rewards. In this case, we do it. Uh, okay, I put through on a call up, and just now it is finished. Let me check the output quickly because that will be for the session. Okay, nice. Not as I expected, but nice. So sorry, I wanted to check this. Oh, no. Okay, nice. We can return to this. Um, it is not a company, more like an organization. We collaborate with different organizations to educate people on AI safety. Oh, that's amazing. More amazing, I would say. I will prefer an organization than a company, but I don't want to take up your screen time talking about that. I'll have to chat about it on Discord or somewhere more relevant. No worries. I mean, one of the biggest parts of this stream is to connect with the people. But yeah, you're right. We could discuss it later. I will have a mini event tomorrow, so if you want to hang out on the voice channel, I'll be glad. So returning again here. Um, I know these maximize the miracle reward. It is set by us as the programmers, but first we need to understand that are some parts, some agents, let's say, no, yeah, some parts that compose the reinforcement learning. These are agents, meaning, for example, the AI and the environment. I think, in my opinion, that creating the environment it is like the most complicated thing here under reinforcement learning. Uh, we talk, for example, that the downsides of sorry, the turn down unsupervised learning, and even with unsupervised learning, the thing with these two types of machine learning is that you require a lot of data, and the common say it's garbage in, garbage out, right? Because if you pass bad data, then you receive bad outputs, garbage outputs, garbage in, garbage out. Well, with reinforcement learning, you don't need that much of data, but you need to model the environment completely. And well, for example, let's think of some examples in where reinforcement learning scenarios can do very well. And this is the chess, for example. I cannot remember the other stream you guys told me, but I cannot remember it now. But the artificial intelligence that beat the chess champion, I think it was Deep Blue, um, was trained with reinforcement learning, right? So reinforcement learning means that in another approach, using, for example, um, supervised learning, the algorithm will have or will need a lot of images or videos or any um, source of data trying to understand how to play chess in and I mean really tons and tons of data like you cannot imagine for being the world champion, right? For beating it. But with reinforcement learning, what we need to do is to model a chess game, meaning the possible movements, the rules, even for example the chessmate or the this scenario where they play. Um, Trying to model that, it's like the complicated part. But once you have it, you don't need data because you generate it. I mean, think it for yourself. When you started playing chess, the first game you play, you probably lose. Even more if the person that it's teaching you, it is bad, right? Well, not bad, but uh, he knows what he's doing, and you don't. For example, I remember when I started learning chess, the person who told me how to play, we start with only the front row, then the horses, then the towers, then and we were adding more and more and more. But that's an approach. I mean, when I started playing, the more I played, I become a better player. Well, the same happens here. If we model these correctly, the agent will know the environment on how to play, and we will have to define correctly the rewards, and in this case not a punish but the punishments to make the artificial intelligence good in how to play. um, and we as humans have a learning rate like very good, right? We learn correctly without we get the idea, once we know what we're doing, we don't take that much time to learn. Well, the advantage of the artificial intelligence is that the artificial intelligence can play a lot of games, very fast. But the disadvantage is that we need to make sure that the artificial intelligence understand what's happening. So that really depends in a lot of things, how we declare the metadata, but also the type of algorithm we're applying. We could apply algorithms based on tabular solutions, based on approximations, and even based on neural networks. We can apply even deep neural networks. Remember, deep neural networks are the ones that doesn't require us to feed them with the meaning features of the data, but they learn to identify them thanks to the complex architecture of the layers. So I see there are some comments. Let me check them. Hey, I am new. Hello, Gus Scholar. I'm good. Sparky Search student. A professional example. It's a nice thing to see at Global Hack Week. Yeah, I do agree. That's why I was discussing with Bryson. Um, Control B says hi. Spark User Goes Student says welcome. Agreed. Humans generalize really well, and we don't need that much specific data. Thanks. uh, Starfire Go Atari games. Yeah, exactly. So the main idea here is that games are a really, really good example on implementation for um, reinforcement learning. But not only games. Well, it depends on your definition of games, right? For example, think of these robots that vacuum, a vacuum robot. If you have or have seen a vacuum robot, you will know that the robot starts mapping the room, and some of them has control that make them like clean the room automatically. Um, I remember my father had one of these, and it was really surprising for me as a child seeing that the robot created like a map of the house, uh, and well, at that point, the robot was not that intelligent, but the map helped him, or help it to trace the security zone, for example. But now with artificial intelligence, this could go way further than that. The robot can understand the room size, like the most accurate paths to start cleaning, because if you have seen them, they start like turning in circles and then going one direction and then going in circles and then going other one direction and then and that is like you don't clean that way. It is not like the best way to clean even, because if, well, I don't know for you, but I like to go like straight and return, and then like, and I draw imaginary columns on the floor and I start vacuum them. Well, the robot with artificial intelligence, this vacuum robot can start learning this patterns to trying to identify a optimal way to do this with less effort without having to to move um, how to say this without having to move and waste energy in parts that it does not need them. Um, and a no pilot car like Teslas, like these kind of type of cars from Google, from I think Apple wanted to create one of them, but for example, Tesla, no, right? Reinforcement learning, I think, will be the best approach to try to tackle this problem because you again that's why I say it depends on what you define as a game, but as a simulation, these cars can be trained in virtual environments and then proved in real scenarios. Uh, and well, the main idea here is that we don't need uh, tons of data. We can start teaching and really teaching the machine on how to learn to do specific tasks like playing a chess game, like playing a video game, like vacuum our houses, like driving us to anywhere we want to go. That's the big thing with reinforcement learning. I really like this type of machine learning. So there's a lot of truth there. I would one thing: your reward function should be very well thought out. Otherwise, your reinforcement learning agent might have some complexity and unexpected behavior. I would add one thing. Oh yeah, yeah. Thanks for the comment. It's really true. And talking about this, let's explain now these elements of reinforced learning, right? We talk about now the agent and the environment. I think those two are really, really clear. Uh, but there are four or more that we can identify. Do we have the policy, the reward system, which is this thing Rainzone is talking about, the value function, and the model. This last one can be optional, depend on the environment, but let's see what they are. The policy is like the policy defines the learning agent's way of behaving at a given time. What does that mean? Like the game rules, for example. Roughly speaking, the policy is mapping from the perceived states of the environment to actions that can be taken where the agent is in those states. So the reward signal, it's defined as the goal of the reinforced learning problem. One of each and another acceleration here. We can define this as steps and as cycles, right? So imagine, again, let's return to the chess game. Could you say every move could be the cycle, or every game should be the cycle? I think this is depending on you, but I think it could be more accurate that the whole game will be the cycle. So again, the rewind signal on each time the steps, the environment sends the reinforced learning agent to a single number called the reward, and the the agent sole objective is to maximize the total reward that it receives. So here it is referred to what Rainson was commenting. We have to make a trade-off, because if we want to be like safe, if we want to define the system not to explore, for example, to take a safety path, it probably never be able to complete or to win or to do the task we want. And on the other hand, if we explore too much, the artificial intelligence probably will understand at some point that to take many paths will be good. But for example, imagine in one of these paths, if this were a maze, one of the paths leads to the out of the maze, right? So the next time the artificial intelligence plays that game after completing it, after going out of the maze, uh, it probably will not take the exit because it's going to be like, hey, I'm going to explore more, and the other time the same, and the other time the same, and the other time the same, which is great. But at some point, we want this to complete the maze, not to explore anymore. So there's the trade-off, and there's the parameters we need to move based on the reward signal to make this right, to make this possible. I mean, so whether the right signal indicates what is good and immediate and immediately sense. A value function, the third element, specifies what is good in a long-term run. This is the state of the total amount of reward the agent can expect to accumulate in the future. Remember this exploration between conservation. And lastly, the the model, which is the fourth element, it's something that mimics the behavior of the environment. In more general terms, this allowed interference to be made about how the environment will be behaved. For example, given a state and an action, the model might predict the result of the next state and the next reward. So these models can be used for planning, and by which we mean any way of deciding a course of the action. And I want to show you now. Let me start presenting my screen. But I need to move this. Give me a second. Okay, nice. A graphic way of seeing this. So we have the agent. The agent contains the policy. We have the environment. I choose this on purpose because you look, this is artificial intelligence. The environment, and the environment give us the observation and the reward. The agent indeed takes action on the environment, and this loop, it's what the it's what the reinforcement learning flow will look like. This cycle agent environment, it's all what reinforcement learning is. Um, we can think of this also if you think of mathematical approximation. Have you heard of Markov chains? If you haven't, it is like an statistical cycle. I remember I watched this topic when I was looking for, sorry, state machines. Yeah, for example, in electronics. So there's a chain that gives action to the next one based on a current state. So the probability of, for example, moving left or right on a maze, moving front or backward, um, at some point, the whole Markov chain will have a full probability of one. I mean, one of them has to happen. Um, but there are some events that have more probability than the other. We are going to move that values on a Markov change, and depending on these rewards and observations, to take actions, right? So that will be it. For example, Sparky Circuit students mentioned something interesting, like the feedback, for example, on a closed loop game. Um, I would say, yeah, something like that on control systems. So it is something that we have seen before, right? So that's why I think reinforcement learning again, it's so beautiful, because I think one of the most beautiful things in life, I think, for example, these like when in physics they discover something, like it's just that simple, like the law of gravity, like this kind of stuff. uh, it's like it's been there. We didn't invent it, we just discovered it. I don't know, maybe. So generalize poly iteration, it's a other thing. Let me check. It's this other thing I was talking about with Markov change, for example. um, mm, I think this, for example, this could be, we have the model, the policy, the body of the function, the policy evaluation, the policy improvement, and the actor. But I want you to take a look to the symbols. We have the policy as the P and the body information as Q. So P evaluates to B and the improvement. So we make this evaluation every cycle to start deciding what we need to do. This it's the policy, um, how to say this, like the policy iteration. It is generalized because we can do this depending on the algorithm. And for this specific case, we are ready to start going on the action here. We are going to take the Monte Carlo algorithm. So we need to define this algorithm with a view like this. Let me. I can make this bigger. Give me a second. Okay, so here it is. This is the Monte Carlo algorithm initialization for making predictions on the reinforced learning, right? And to continue with this session, I want to say that we are going to use this algorithm to teach an artificial intelligence how to play poker. No, it is not poker. It is blackjack. Sorry, uh, card game. Well, in this case, we define the input. The input is a policy P to be evaluated. We initialize this from estimating the B. In this case, if I can remember, B, it is. Uh, give me a second. I have my appointment here. The value of the state and the reward that it's hoped for an state. In this case, we can approximate from the experience, but every occurrence of the states S, um, B function of S, it's an episode, and we need to visit the S. We do it first visit versus every visit. So this will be the first visit algorithm, but here's the how to be every visit. Mm, mm, Give me a second. I think that I don't have the semi-code for that, but we can go with the first visit. So this is an arbitrary for every episode, and for this Monte Carlo estimation, every episode it's independent. Um, if you know the game, you probably know that, for example, there's a set of cards and you can start counting, because when a card appears it can only appear four more times until the deck is done, right? But in this case, this will be an ideal scenario where the cards are infinite. So that's why, in this case, every estimation is independent. So we don't need to keep track of it. And the computational needed for this will be the same amount for every independent state. That's another good thing. Then we need to define another thing that is Q. Q it's the return that it's when the state S takes the action A and follows the policy. Um, Give me a second. I don't have that around here. Mm, yeah, this. So this will be the improvement of that. We have our initialized arbitrary p for every state, the q, and returns. So we need to loop from each episode. We define the number of episodes. Remember, more episodes meaning more learning. Not in all cases, but supposed to be. And we choose the S0 and the A randomly, such that all pairs have probability of occurrences, right? So these Monte Carlo policy evaluations experiment lots of episodes with the value function to be close to what we want the function to be, and the policy improvements making these greedy policy respect to the value function of the actual value. Now, these it's called the exploring starts. So we can grant that each pairs of these S and A will be visit or will be a thing that the AI wants to take again, the exploration part, in an infinite number of times. and that the limit being the number of episodes. Infinite, this is why it's called loop forever. It's between quotes. It cannot be infinite, but it each episode it's going to be exploring these pair value SA. So then each pairs S and A has a bigger probability of being zero, so that we can start checking them. We can take another estimation for this, which is the on policy first visit, um, meaning that in this case, we just going to visit them or call them on the first visit, but we can check that further later. Right now, we are going to explore do the exploring start, which is the model I have prepared. And well, at this point, I know there's a lot of information, and this is the heavy stuff. But on the code, this will make more sense, right? Um, I hope every one of you knows how to play blackjack. If you don't know how to play blackjack, well, the thing is, it's a card game. You have to be closer to the 21 value. Each card represents a number. I mean, the deck has A's, 2, 3, 4, 5, 6, 7, 10. Then J, Q, and K, meaning Queen, King, and Joker. No, it's not Joker. I don't know the other name in English. But the thing here is that numbers are the number, letters it's 10, and the A's it's 1 or 11, right? Um, you have to have a closer value to 21. If you go more than 21, I'm meaning 22, you lose. If you go less, well, the one with the closer value wins. You play again against the house, so you can hit to ask for another card, or stick to go with the cards you have. We will be defining the rewards as -1 for when the algorithm loses, a +1 when the algorithm wins, and a 0 because they can tie. Then again, the actions can be hit or stick. That's it. Once you stick, you flip your cards, and the states of this can be the sum of the cards of the player and the visible card that has the house. This is around 200 states, and well, that's how the game works. Let's take a look to this in the collab. Before that, let me check for here the comments. Is there any particular site resource that'll help you better understand those markup chains you were sharing? For specifically for the markup chains, I don't have them. Like I watch them on the university, but I just have like appointments and that. But I don't take that much. I don't take good appointments. Notes, sorry, not appointments. I don't take good notes. I will recommend you to watch videos on YouTube. Like that will be the greatest thing. But no. But if you mean for resources for reinforcement learning in general, yes. Actually, the biography I am currently using, it's really great, and I don't fully understand these in the whole complexity, but what I understand it's thanks to this. The book it's called reinforcement learning and introduction, and it's from Richard S. Sutton and Andrew G. Barto. Let me share the bibliography here. Let me just give me a second. This one, it's really cool. What do you think about energy consumption to maintain database? Um, Energy consumption in all of these computational miracles and challenges, it's very it's a thing to have in mind. Um, Thankfully, there are dedicated fields in investigation to try to reduce them a lot, but a lot. And also, it's up to us in our responsibility to not just say, I can train it. Uh, I don't care if I check the data. I can retrain it again and retrain it again and retrain it again and retrain it again. Be responsible of what you consume. Um, in all senses, like in food, in water, in air, in like the packaging of what you buy, like uh, 10 boxes for a SIM card, uh, how big carbon for your giving just for ordering things in Amazon that you could buy yourself on your way to work and stuff. um, and that includes when you're a developer, the energy consumptions of your models, of what you're developing, or of your databases. If it is not just a matter of efficiency, like my query was resolved or was fulfilled in 0 to 0.0002 milliseconds. That's great because you get your information fast, but that's also very great because you spend less energy and computational in computational terms, right? Well, same here. For example, we were talking about these different types of um, of, of approaches of the Monte Carlo method. The first visit, the exploring starts, and the one start. Well, the most efficient one will be the last. Will be the sorry the let me remember. Well, I don't remember. Check it again. The first visit on policy control, because it it means the function will be invoked less times, so we will need less computational effort for this. So that's what I think, that we need to be responsible of this. uh, Consume less in I mean in program, in all ways of speaking, but in this particular sense, in programming speaking. Thanks. No, that's okay. So now, yeah, let me share this. So first, we will need to install Swing, Box2D, and Gymnasium. What's Gymnasium? Um, well, take a look yourself. Oh, probably heard of this before. It's an API standard for reinforcement learning with a diverse collection of reference environments. So this is the great thing. Remember, trying to, well, not trying, creating the environment. It's like the heavy stuff here. and thanks to gymnasium, we can take the environment, and for example, we are going to use these uh, toy text blackjack environment for us to play, because it contains a lot of things already made. But for example, actually, that's what I want to do tomorrow. I want to take these Atari, because this black chip doesn't have the visual output that beautiful, but this Atari one with the card card no box to the car racing. This is the one I want. I want to do this tomorrow for part 2. So not with the Monte Carlo, but we can try to create a neural network, or trying to do another tabular solution for this. And the main idea is you can't see it here because the car is not moving, or it's moving too slow, but we want the artificial intelligence to learn how to race this car. Lunar lander, yeah, space hunter, yeah, a lot of great things here with the Atari one, right? So yeah, the gymnasium API help us to do that. And the other thing you probably are wondering, didn't ask before because you're so polite, it's, hey Alberto, I think it's the first time I see you doing a collab. Why not on locker environment? Because you always do that on your own machine. Well, thanks. The thing here is that these kind of models start being very heavy and very specific, and said that um, trying to train these models with the machine I have, it is not impossible, like in computational terms. I mean, I have a good machine, but it is impossible on architectural terms, because it's this model, it's prepared just for being trained on a GPU for NVIDIA. We discussed this on one of the sessions of the week. I don't remember which one was, but the thing is that it's impossible to me to run this on an Apple Silicon chip. So that's why I'm using Colab. Plus, it's good. It's great, like to have the the output or the computational effort being processed by another computer, not yours. So once we have that install, like Swig box engination, we import gym nation as gym, numpy as mp, the collections of the default dictionary, matplotlib 3D as axis 3D, matplotlib as plt, and cm and other lines we have. We make a function that it is going to be called make graph, and we pass a q function. This is let me close this one and let's drink some water. Well, this q is the same like the one we're watching here. The hoped return of the state. So in the range of 12 to 22, which is sorry, PS and DS, ace, no ace. We want to check if these were aces, ounce, ace, append, match grid, figure. Okay, you will understand this function to create a graph, but what we are going to represent here it's these functions. Let me see if I can check this. This is again on the book here. Okay, this disappeared. Okay, nice. So we are going to give two graphics with an usable ace and a not usable ace, seeing the dealer based on the card the dealer is showing. I mean the house. That's with the player sum. The lower axis means it's a learning rate not acceptable or it failed. I mean, sorry, the -1 we declared -1 it's the computer lost and +1 it's the computer win. Remember, 0 will be it was tied. So if the dealer is showing an ace, probably we as humans will say I stick or I don't go. Like I don't have possibilities of winning because this is a very good hand. Or the dealer is showing a 10 or what they are showing, right? Um, and this is pure, how to say this, uh, pure graphic way of representing the learning rate and how the artificial intelligence did. Like if the graphic goes from low to high, it means it start losing. Then at some point it start winning, 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 and now the only thing he knows or it knows is how to win, right? So that's what we do here. That's why we declare the PS and the S, and we separate them on the range of this. And we have a list for when it has an ace or we don't have an ace, because that's another very important thing. Well, in blackjack, I mean, not in computational terms. We have an act space where turn 0 and 1, and meaning hit stick or hit. We resume. We have an argument max. Um, in this case, I use this because I call the other functions here on argument max get action. Where I call this. Hey Alberto, do you mention the code? No, of course I can share this. Give me a second and I will share it at the end of the session, right? Um, or right now, right now. So here's the collab. And give me a second, I'll be back. I need a quick break for something. Take a look to the code and I'll return in couple of seconds. Hey, I'm back. Thanks. No worries. Um, okay, so I was explaining these RMAX. So let me see where I call this to refresh my memory. Okay, max A star. Okay. Yeah, no, I remember. Remember this little part here? We need to understand that each function here does something of this semicode. So this argmax is exactly the same. I mean, for this policy, it's to be evaluated on the argmax A of Q, S, T, and A. ST meaning the T, it's the occurrency for the S, and we need to remember that the S it's the episode. A in this case is the visit, and Q it's the expected return. So returning to this, we pause the argmax function, same and in this here, we pass the st, um, the action a, the episode, but now we pass q, action and episode. Okay, well, in this case, in act space, I mean, the two scenarios we can say, we create a tuple as A and we ask for R and that Q containing this tuple. If R is bigger than the max R defined, so the max R is going to be now R and the max A is going to be now A. And we return, that's how we say this is going to be the max Q, called the max A. The action, we pass the ops, meaning the state, and p. In this case, p it's completely the same one, the policy. So we need to modify the policy at some point. This is the update the p. For updating this p, we pass the action in the space state, and similar, we create that tuple for checking if this is the max or the a we want to approach. If not, we change the p based on that. Then we make the episode, and this episode will be like for actually this will be happening every loop, every iteration. So we create this list and we set the um, the state to be reset, and while we get the observation, the action, and the reward, this will be defined for the dictionary step. So every episode will we have a step dictionary, and we return this episode. So that this is like the functions to help, but the main code or the main idea goes here, and this is what this semicode replicates. First, we need to initiate the environment of gym. So we make gym dot make blackjet versus b1. This is going to be natural false and self false, meaning that we don't want the pretty output. Plus, this is a collab, so I don't know if that will work either. Then we declare the policy without the file dictionary of the length of the arc space. We declare the expected output. Same with the default dictionary, and we return. This returns. It is an empty list, just like that default dictionary of the empty list. We define a number of episodes. In this case, I'm proposing 50,000. That was good to me. You can do less, you can do more. If you do more, be caution because sometimes this takes time. This is the call up I put to run before the session, and I interrupt to check the result. Then we define gamma, which is this value, and an epsilon, which is this, gamma. One of these is gamma, another epsilon. I can remember. Choose. Okay, but what those things do, it's like to help their learning rate. Um, And for the number of episodes, we make the episode function with the environment and the policy. Then we, in this case, this is generate an episode from the SA following the policy. And we create G0, that's the literal way. Um, I don't remember what I added the visit, but I think we can remove this. The step is set to be the same thing, append G to returns. In this case, we append G to returns. But before that, G is going to be gamma G plus the step R. In this case, the iteration, since Python is zero index language, that will be fine. We don't need to add another index. And the S of this, it will be the step S and the step A, this tuple, remember? Because we need to append the returns of the tuple to G. And the mean of that The average of the returns tuple will be stored on the queue every time of the episodes. Remember, that's the episode, the action, and every time we modify in this function the policy. That is here at the end. And we update this policy with the max a argument. Then finally, with the queue resulting, we have all the information that we needed uh, to see the result. So we close the environment and sorry to make the graph, and we close the environment and we checked that, for example, here when for a reason with no a with well with aces and with no aces, the model tend to lose when house or the dealer has low number or high numbers. But it starts learning, and now the result it's great because this meaning the result it's closer to 21. That's what we want actually. More occurrences here, uh, and that's it. I mean, having the ability of doing this, and then we can put this in practice for the model to play. That's the challenge. And well, why Monte Carlo? You may be questioning yourselves. Well, it is not like if it is the only algorithm. Actually, it is not even the best algorithm. We can see this um, takes more episodes, and the result is not that good. I mean, this was a decent result, but we can easily make this curve uh, in turn. Okay, don't worry. We just need to reconnect. Yeah, we can make this graph to be softer because we've seen some peaks here, and that will be with another model that well can be the approximation methods, like what could be mm, we can discuss. Well, we can apply different models. That's what I'm meaning. And well, that it's all I have prepared for this session in this part one. Um, it was fast. I think so. You have any question? I will be happy to answer them. Um, I know the code. It's not well documented. I'm sorry. I will try to document it better. But the explanation of the function here hopes that it was good, and see the semicode here being implemented of this actual Python code. That's the other thing that helped. So let me close this, and let me see if I can show you another interesting thing before we go. Mhm. Let me see if we can make this the visual example. Okay, yeah, for that will be here on the card. Type text, blackjack. This environment is part of the environments which control. Okay. hmm Face cards have a point of 10. Number of cards have. Okay. I think I should check then. Um, Gymnasium make the observation space. It's tuple, discrete, the action space. Oh, look, they have here the same image. hmm But this would whether to follow exactly rule. If SAP it's true, the keyword argument natural be ignored. If the player achieves a natural blackjack and the dealer does not, the player will win. The reverse rule does not apply. Okay, that's not what I was looking for. make episode. How much proficiency in Python it's needed for doing ML stuff efficiently? I will say not that much. I mean, Python is not my like natural language languages, right? That Python is not my first language. What I mean with that is that I don't speak Python fluently. Um, I do a lot of JavaScript, but a lot of JavaScript, and I love it. And Python, I not say I'm learning it, but sometimes I have to Google a lot of stuff. I ask Pilot, but a lot of help. And the thing it's not knowing Python. The thing it's not the actual ML stuff. So don't worry. Plus, if you start doing ML with Python, at some point you will have to learn very good Python. So that will be the answer for that. Create grids. Look at this curve, for example. I mean, this is not that. Um, it doesn't have that much noise here, and the learning rate here. I mean, the going from a low level from a big level, it was much faster. So that's a better result. And maybe they do more training epochs or episodes. Sorry. So that could be it. But what I wanted to do is to take a look at this environment, and I don't know how to do this. Actually, I haven't tried before. I was doing this on live. Um, so let's try it. Gymnasium visual repress visual animation. Uh, this is gymnasium first learning visual animations. How to show, and I look at the previews of the environment to show the episode increases in the animation on the bottom right corner. So I'll comment to explicit show that. Amp render. Okay. Amp render. Now we're talking. Human. Now we are talking. Human. Does this works? No. Call embryo before call it's the indeed okay. This is a problem. For each step, you should obtain the frame with grander RGB array. You convert the frame and reset, then um, render. Okay. This is reset. Okay. Node. Okay. Okay. Computer render frame as specified with render mode during the initialization of the environment. Uh, so when this is initialized, okay, says that save random agent give. Hmm. So maybe I can see this here. Q-learning. Yeah, this is another model algorithm. Sorry, that it's not Monte Carlo. That's probably why the um, result it's better. I just want to see how to display this. No, this is broken. I really want this thing here, like how it's happening. Yeah, working as a freelancer, I make a character artwork logos better. Neither work to build my own experiences. Do let me know if anyone it's interesting. Thanks. Hey, so if anyone, uh, where they can contact you, buddy, visualizing the training, mm, visualizing the policy. That will be very similar to this. This is the policy. I think you can do better. You can visualize the environment using the play function. I don't know. I don't believe you. Play function. I didn't see the play function. Um, Come on, I want just the visual. Wait, let's try. We can close this visualizing. We build the agent, execute the action. Okay, during step and render. Come on, it's executing now. Shouldn't I be seeing the output? I said human, right? So why? Okay. To be honest, I am not sure if this is something that is possible. uh, do you have some work for like shifting at last 3 months? And thanks for the promote, bro. Do you have some work for me? I would shift in Atlanta. My God, I'm still trying to find jobs and my paying bills. Yeah, no worry. Fortunately, I don't. But well, again, the community is always good to share, and so you go share your LinkedIn and start connecting with people. And well, the Discord server is always there. Just follow the rules, and I don't see any problem for you for ask for any referral or something there. And I hope you find you have some gymnasium with rappers, human rendering. What do we need to metadata field for? I will try to do this not on while I'm in here, but on my computer. I don't know if that's it. I mean, that's the problem. This still running, you know. um, Basic usage, compatibility with June. Okay, if we look at the previews of the environments, they show the episodes increasing in the animation of the bottom right corner. Is there a command to explicitly show that? Is that directly available? For each step, you obtain the frame. Okay. You convert the frame, which is an internal array, into a PL image. You write the episode name on top of the PL image using utilities. Okay. You save the label image into a list of frames. Okay, you render the list of GHW using MATLAB utilities. Okay, I will have to put a pin on this so we can check it tomorrow. And well, the blackjack, unfortunately, it is not that complex, or fortunately, I will say. So these graphics already told us a lot of information of how this model is playing the game. But for tomorrow, for tomorrow, we will be doing this documentation box to the car racing. So this car racing, that will be a very interesting to see. The action space it's bigger in this case, so we need to define that. Um, and well, that will be it. So see you for tomorrow's session and this part two on reinforcement learning introduction. So we checked the theoretical concepts in this session. We checked an algorithm, which is the Monte Carlo, and we checked a practical example on how to put an artificial intelligence to play blackjack. Tomorrow, we will take this to a more graphical environment, and we were going to use the Q learning algorithm for that. And we are going to teach this little racing card how to race. Um, and that's it. Thank you a lot for joining me. I am sorry for not putting this graphic on the blackjack one, but well, that was my bad. But I hope you learned something from the reinforced learning session, and that's it. See you. Thanks a lot. Unless you have a question, so if you have it, comment it. I will give you some time. If not, well, again, thank you a lot. No, thanks to you. Okay, I think it is no more questions. So bye bye.